Okay. So starting off with uniform distribution. So uniform distribution is mainly of two types. First is the continuous type. Continuous uniform distribution. Continuous uniform, and then we have discrete uniform. Okay, so it's a very simple distribution. So as the name suggests, the uniform. So here the probability will be uniform in each case. So for continuous case, if you look into the continuous case, how it will be something like we will be having a specific range. So let's say the probability the it's a as I said, it's a continuous random variable, and we can also call it as a rectangular distribution. And here the rectangular, that name comes because we will be specifying a particular range. So for example, let's consider an experiment where there is an arbitrary outcome that lies between certain bounds. So that bounds are defined by parameters a and b, which are the minimum and the maximum value. So if you are specifying a bound here, let's say the bounds are a and b, and we will be only having non-zero values in between this bound, zero I mean a and b. Okay, that is the meaning of this notation. So if we draw that, so since it is a continuous case, we will be making use of probability density function. So let's say this is A and this is B, and we'll be having a PDF function of this sort. And similarly, if we draw the cumulative density function, so as we discussed, the cumulative density function, it combines the probability from the starting observation till the last observation. So if we look at, I mean, if we do cumulative density function in this particular case, it will be having non-zero values from a. So till a the value will be 0, and from a it starts to increase, and when it reaches the point b, okay, then it will be 1. Yeah, so this will be the cumulative density function. So we can also like represent this probability density function as 1 by b minus a for x between a and b, and 0 elsewhere. So the next case is discrete uniform distribution. Okay, we can also say we can also cover how this mean and variance is in this case. So mean in this case, so it will be 1 by 2 a plus b. Median will be same, 1 by 2 a plus b, and the variance in this case will be 1 by 12 b minus a the whole square. So for this particular case of continuous uniform distribution, we can assume it as let's say the number of candies sold daily at a shop in a is uniformly distributed. Let's consider that number of candies sold in a shop is uniformly distributed, with a maximum number which is 40 and then a minimum of 10. So if we are considering that particular case, then it will be starting from 10 and then till 40 it will go. So till then it will be having a probability value, but then it is happening with a uniform probability. So every point will be having same probability. Okay, now let's consider the case of discrete. Uniform distribution. So as the name suggests, here it will be discrete cases. Earlier we had continuously varying continuously varying points or random variables, and each point had particular value which is equal. So earlier we had 1 by b minus a. In this case we will be considering a discrete case. For example, let's consider the example of rolling dice. In that case we have 6 different points. So 1, 2, 3, 4, 5, 6, and each will be occurring with a probability of 1 by 6, right? So in case of rolling dice, the observations will be 1, 2, 3, 4, 5, 6, and here the probability will be nothing but 1 by 6. So if we draw the probability density function, no, here the probability mass function, because it's a discrete case, it will be 1 by 6 in each case. So 1, 2, 3, 4, 5, 6. Each will be having value 1 by 6. And here also the notation is similar, U, A, B. And here since the value for A and B, here it is nothing but the starting value A is like here we are considering the total number of observations. So in this case we have 6 observations. So it will be B, which is 6, B minus A plus 1. So it will be 6 minus A, which is 0 in this case. So 6. Sorry, this is 1 by 6. Okay, so this was a simple distribution, the uniform distribution. This we will find in certain number of cases as the example similar to the dice, or even in case of coin, it's a uniform probability 1 by 2, 1 by 2. So there are certain examples which are following uniform distribution, but it is not a often seen distribution in the real world data sets, but there are few cases which are following uniform distribution. And then the next probability distribution which we'll be looking into is log normal distribution. So in probability theory, a log normal distribution is a continuous probability distribution of random variables whose logarithm is normally distributed. So here it says that logarithm of a particular random variable is normally distributed. So thus, let's consider a random variable. We are considering it as x. So it says that log of x is nothing but it's normally distributed. So if log of let's say if log of x is y, then what can we say about x? So we can say x as yeah, so okay, then okay, just give me a second. Okay, sorry, so I just made a mistake here. Okay, I will just read the definition first. So in probability theory, a log normal distribution is a continuous distribution, probability distribution, where the random variable whose logarithm is normally distributed. If the random variable x is normally distributed, then y is equal to logarithm of x has a normal distribution. So here it says that if we are considering a random variable x, and if this x is log normally distributed, then its corresponding quantity y, which is equal to logarithm of x, then this y will be normally distributed. So this is the relationship over here. So it says that if we have a log normally distributed random variable which is x, then its corresponding quantity y, which is logarithm of x, that y parameter will be, or y random variable will be normally distributed. And in all the cases, this log normally distributed function or random variable will be a right skewed distribution. So it will be having a tail towards the positive end. And this will be the distribution for x, which is log normally distributed. Correspondingly, if we are looking for the distribution for y, in this case y will be, as we said, y will be normally distributed. So just remember that all log normally distributed random variables will be having a right skewed distribution, and the parameters will be same, like a normal distribution. We will be having mu and sigma, and here also we will be having some other mu1, sigma1, because both are normal distribution but then with different mean and standard deviation, and the log normally distributed one will be right skewed, and the other one, which is corresponding value, will be having a normal distribution. And we will check in detail how we can confirm that a particular uh, random variable is following a log normal distribution using QQ plots, that we will do in the later sessions, where we will go deep into the data science part, and we will see in detail how we can check the QQ plot. We have a specific functions in Python where we can check the QQ plot and say whether random variable is normally distributed or log normally distributed. That we will see in the later sessions. So for this case, we can consider some very simple examples. Let's consider the wealth distribution of the world. If we consider the wealth distribution of the world, it says it will be always of a log normally distributed fashion, which says that most of the salaried class will be having will be in a higher position, like if we draw the log normally distribution, it is nothing but of this shape, right? So there will be a very few number over here which represent the rich people. And there will be a there will be more number of people who are salaried or in the upper middle class or middle class, and there will be like this will be a distribution which we can think of when we are when we are thinking about log normal distribution. And similarly, we can also look for example where we are looking into the comment section of a discussion forum. In that case, there will be people who will be like writing just with a reaction. So there will be so many people who are putting just reactions in the comment section, where there will be also people who are writing very large comments. So that proportion is very less, right? So if we are considering that example as well, we can also consider that as a log normal distribution. Or else we can also think of example where we think about the dwelling time. So dwelling time is nothing but the time which we send on different platforms, for example Instagram or any other social media, so or websites. So that also comes with the similar log normal distributions. So now let's go to the next distribution, which is power law distribution. Power law distribution, it's very useful, or it's something which we always relate in case of certain process optimizations or finding out root causes. In all those cases, power law distributions play a very good role. In statistics, a power law distribution or a function is a functional relationship between two quantities where a relative change in one quantity results in the proportional relative change in the other quantity. Okay, for example, let's yeah, let's start with the shape of the function and then we will explain how the case is. So the function will look something like this. Mm-hmm. And if we look into this is around 20 percentage of the data, right? This part contributes to 20 percentage of the data, whereas uh, this is around 20% and this part is around 80%. And power law distribution says nothing but the total cost will be majorly due to this 20 percentage. That is a simple explanation which we can give. So the I can read the definition again. In statistics, a power law distribution is a functional relationship between two quantities where a relative change in one quantity results in a proportional relative change in other quantity, independent of the initial size of those quantities. One quantity varies as a power of another. So if a small change is if something is not under control, the major contribution will be coming from the 20 percentage. We don't have to go and check the whole data. That is a simple explanation which we can give in this case. For example, let's consider a similar example which we considered earlier. 80 percentage of the wealth are distributed with 20 percentage of the total population. That example we can also make use here, where where as I said earlier, it's like the 80 percentage of wealth is fully going to the 20 percentage population. So if we are looking into the wealth distribution, then again this 20 percentage is making more effects or more changes in the overall process. So we can look into it that way. And similarly, we can look into another example where the 80 percentage of the total is with 20 percentage of the nations. And if we look into that case, okay, with that 80 percentage of the total oil, that 20 percentage of nation is making bigger advancements or bigger economic advancements. We can consider, if we are looking into that example, we can think of it that way. And we can also think of, let's say we are when we are speaking, the frequency of words which we are using. There will be words which we use more often, and there will be words which we will be using very rarely. But that rarely used words will be the ones which will be giving the effect or the meaning of that particular scenario. Mm-hmm. Yeah, so those are certain examples which we can look into into this in this case. Okay, so now we have the next distribution, which is Pareto distribution. It is similar to what we saw earlier. It is similar to the log normal distribution. Sorry, similar to the power law distribution. The definition itself says that it follows the 20-80% rule. So 20-80% rule is nothing but the 20 percentage of the entire data is contributing to the entire process. Mhm. So similarly, the Pareto distribution is any distribution which follows 20-80 rule, and here also we will be having non-Gaussian distribution of shape which we saw earlier, which will be like this. And we can transform a non-Gaussian distribution of this shape into a Gaussian distribution by using a transformation called, we can transform this type of distribution into a Gaussian one by using a transformation called Box-Cox transformation. We'll also see how this Box-Cox transformation is done by using examples later. So to give a small idea, let's say we are considering a process and we are having some sort of a cyclical process. So those cyclical process, how we treat the cyclical process is entirely different from how we are dealing with the continuously varying quantity. If we are looking into a cyclical process, the variables will be changing in a particular fashion in each cycle. And if we do a simple a regression analysis, regression is nothing but we are trying to match the initial x parameters with the y, right, with using some sort of function. So if we are doing it that way, using a simple regression function, it won't give the proper results. So this box cross transformations is very helpful or useful during the cases where we are looking into cyclical data, and that we can see in detail by looking into certain data science projects later in one of the session. And to give an example over here, let's consider the IT industry. 80% of the entire project is done by the 20% of the team. So even though there are more number of workers in a particular team, but then the more work will be done by 20% because there will be others who are doing their administrative works, who are doing the coordination and all those, right? So we can look into that as a simple example in this particular case. And similarly is the case with process optimization. So in case of process optimization is nothing but we are trying to optimize a process. So in that we are trying to find out what is the root cause of certain process not being working properly. In that case, if we are trying to figure out the root cause, we will come to a very small number of features which is contributing majorly to the not proper working of the entire process. So that also can be taken as an example here in this case. So as I said, Pareto distribution is same, almost same as the distribution which we saw earlier, and both follows the 20/80 rule. And here I am,
I
yeah,
can
yeah, please.
I can just add one or two like real world examples of
Mm-hmm.
Pareto distribution,
Mm-hmm.
where like we see that always the rich keep getting richer, and like things like that. So the way it works is, I mean, for example, you need money to invest so that you make more money.
Mm-hmm.
So with whatever you have, the it whatever money begets money. So
Mm-hmm.
in that way, that is how the rich keep getting richer, etc., etc. And no matter what, whether it is communism, capitalism, or any other economic system we follow, the maximum of the majority of the financial assets or economic power, whatever, will be with a few set of people. That is not due to any injustice being done to anyone. That's basically a law of nature. I mean, so
Mm-hmm.
like another example is, suppose like let's say if we see the number of songs being sung in the movies, like so maximum of number of the songs will be sung by maybe 4 or 5 people, or maybe 10 people.
Mm-hmm.
But a lot of people will be equally talented, maybe slightly less or
Mm-hmm.
whatever. But once you get an opportunity, then you tend to get another opportunity,
Mm-hmm.
because you have already got. So that's how, I mean, like I'd read about it somewhere, so
Mm-hmm.
I thought I'll just mention some real world examples of this
Mm-hmm.
Pareto distribution. And yeah, that's all.
Yeah, thank you. Yes, that's really insightful. As you said, like once you are in power, or once we have money, then we can invest, and yeah, it will be getting more and more. That's the case which we have. And similarly, like the other case, yeah, both of them are following the Pareto distribution. And in real world, it is very important. In most of the cases it happens, as I said, the process optimization. It there is for data science role, we can see the roles which is called data science process optimization roles. So there the entire task is to analyze the process, and in that get to understand what is the majorly contributing factors in the whole process. And if we are trying to figure out, it goes down to a very few number of factors. And if we are fixing that particular number of features, then the entire process will be much enhanced, and the number of defects which we are getting afterwards will be much less. And then the process optimization task, maybe you might have heard of courses like Six Sigma. I don't know whether you have heard of those. Yeah, so in that this is the major work they do. So trying to make the entire process with less number of defects and making more efficient processing. Yeah, that is the thing. Yeah, it's very good that you pointed out that, like, getting the real world examples, it's really easy to relate, and it will be there in our mind as well. Yeah. Yeah, so now we are coming to almost the end of this descriptive statistics session. um, we have we have to cover central limit theorem now, and then we have a very small topic which is called estimates. So the next topic is central limit theorem. I guess mostly I think everyone would have studied this during our 12th standard, or I guess so. So the center limit theorem, it relies on the concept of sampling distribution, which is the probability distribution of statistics for a large number of samples taken from a population. So if we are taking samples from a population, the center limit theorem says that sampling distribution of the mean will always be normally distributed. So it says that, let's say we have a sample and a population. This is the sample and the population. And it says that the mean of the sample will always be normally distributed. It says that, let's say this is the mean distribution of sample, it will be always normally distributed. And it doesn't say that the initial population which we are considering, it should follow either normal distribution or binomial or anything. In whatever be the distribution of the population, always the mean follows, the mean distribution follows of the sample follows a normal distribution. That's what central limit theorem says. And there is one condition: if the population is not normally distributed. If the population is normally distributed, there is no other condition. It clearly says that uh, the sample mean will be normally distributed. But if the population is not particularly following a normal distribution, in that case it says that the sample size should be, if population is not normally distributed, in this case we have a specific condition that the sample size, or n, should be greater than or equal to 30 for this particular center limit theorem to stay. This is a condition if we are having a population with any other distribution. Yeah. So we earlier discussed that like it is very important to know the normal distribution. In the when we started the discussion during the normal distribution session, we said that normal distribution is very important because there are certain machine learning algorithms which specifically says that if the data is normally distributed or standard normally distributed. So this particular case of normal distribution is very important. And the central limit theorem, as I said, it comes of interest when we are looking into this statistical analysis and trying to um, infer what is there in the data using some sort of hypothesis testing and all those case. Most of the statistical analysis test make use of this central limit theorem. Earlier, during one of the interviews, I was asked, let's say there is a process, and so the test to check if a particular batch of item is defective or not, that itself is making the item to go defective. In that particular case, we have to say a number, like how much quantity from a particular population should be selected to check for defectiveness or not. So that was the question asked. So we can't always say a particular number most of the cases, but if we are looking into a bigger picture and if we have so many number of samples, it's most likely that we have to take at least 30 from each of the population to get a better understanding. So that was what I was said. um, yeah, and we can look into that when we cover the inferential statistics. During the inferential statistics session, we have to cover all this in a much detailed way. We will solve problems as well. We will get more understanding during that time. Yeah, so that was the main topics in the descriptive statistics. And we can also say one more thing here. For the population, we discussed the standard deviation will be sigma, and in case of sample, the standard deviation we consider always it as sigma by root n, where n is the sample size which we are taking. So this was one more thing which I had to cover. Yeah. And here for sample we can consider the mean as x bar, and here we cover it, say it as mu. Yeah, so that was the main things which we had to cover. And yeah, and the next session, it is nothing complicated. It just says about the estimates. We don't have much to cover here, which says that estimates is specified observed numerical values used to estimate an unknown population parameter. For example, we for a population, to represent a population, we can study the population mean, population standard deviation, variance, etc., right? So those are called estimates. And there are point estimates which says the single numerical value which can represent the unknown population parameter. So as I said, the population mean is a example for point estimate, and there is also interval estimate. So we can say about point estimates, which is a single numerical quantity which can say something about the entire population. And there is also interval estimate. Interval estimate is a range of value which is used to estimate unknown population parameter. For example, in the coming sections we will see a lot of confidence interval, and how that is confidence interval is created, and how to check if a particular quantity is coming in between this particular confidence interval and all those. So those confidence interval um, is something which comes under the interval estimate. And this I covered just because in the next session for the inferential statistics we will be making use of point estimates and inferential interval estimates a lot, and we will be doing problems as well. Yeah, so this comes to an yeah, this makes the end of descriptive statistics. I think we almost covered everything from the descriptive statistics. And as I said, I will make a note of it, and I will share it most probably next week. And once I prepare the notes, then I will share in the group.